Okay, so lecture number 9 is on, we've talked about single agent search so far, meaning we're just trying to guide one agent around. But now we're going to talk about two-player games and the Minimax search algorithm and an enhancement for the Minimax search algorithm called AlphaBeta Pruning. And without any exaggeration, the Minimax search algorithm actually changed my life. It's probably not going to change your life, but it's the algorithm that I implemented for the first time in a course, actually for the second time, but for the first time really well in a course for my PhD. And at the end of that course, I was so blown away by the fact that me as a human, I could write a program that could beat me at a game, that I switched what I was doing from computer vision to AI. And so it literally did, I'm here because of this algorithm, which is really strange. And again, I'm not saying this has to be completely mind-blowing for you, but that for me was just a really cool experience to see you can create something that's better than you at something. And this was a lot more mind-blowing before all these LLMs and ChatGPT were around. And it's such a simple algorithm. It's like 10 lines of code if you do it in a specific way. But it's really cool. So I hope you like it. So multiplayer games. So far, like I said, we've only looked at problems with a single agent. That's called single agent search. Let me just really quickly double check something. Yeah, okay. I wanted to make sure that I was recording the audio here. So we've only been looking at problems with a single agent. Heuristic search can also be applied to environments or games with multiple agents or players in those games. And so just like single agent search environments have a number of properties, so can multiplayer games. So we looked at these before. I'm not going to go through all these again, but different types of properties like the observability, whether or not they contain randomness, dynamic versus static, etc. But also a property are the number of agents in that game, right? So how many players are in the game? So let's look at some examples. We might have, for example, the game of chess or Go, sort of these traditional board games where you have this 1 versus 1 turn-based type of game. You might have a game like baseball, where you have 18 players, 2 teams, only one person is batting, but up to 3 other people can be running for one team, but then the other team fields 9 players, so you can have all these type of different players interacting in different ways. Video games like StarCraft, you can have 1 versus 1, you can actually team up and do 2 versus 2, or you could have like a big free-for-all match where the last person standing wins. Maybe when you're playing poker, you have something like there are 10 people at a table and you're just trying to make the most money, etc. So the number of players in the game is going to affect a bunch of things, but mainly the type of algorithm that you would be able to use to try and come up with a solution to that game. In the last lecture, we talked about payoffs. And payoffs are essentially a numerical representation of what each player is hoping to achieve in that game. And we looked at that when we talked about matrix games from a game theoretical point of view. So some examples, in the prisoner's dilemma, we create that matrix with numerical payoffs. We're trying to just maximize our payoff from that. In poker, maybe we're going to assign some numerical value to how much money we have won, and we're trying to maximize profits. But in a lot of games, like a board game like chess or Go, or a video game like StarCraft or League of Legends or whatever, it's just win the game, right? And so we may do something like assign a 1 to a win, -1 to a loss, and a 0 to a draw. And so we do still have to assign payoffs to these games. In game theory, I meant to say this in the game theory lecture, but I forgot. There is a concept of a zero-sum game. And in zero-sum games, each player's gain of loss or payoff or utility is equally balanced by the utility of other players. And what that just means is that if you gain something, then I lose that thing, if it's a 2-player situation, right? So all of those payoffs are balanced. So in a game like chess or Connect 4, which we'll be talking about for our assignment 3, we're going to assign like a 1 to a win, a -1 to a loss, and whoever gets the 1, the other person gets the -1. And so whatever the reward, or so whatever the payoffs are for that outcome of the game, they're going to sum to 0 for both players. And an interesting property of zero-sum games is that for any zero-sum game, a Nash equilibrium exists. That's just a property that we're not going to prove, but it's cool. So for most traditional board games, which is sort of where we start with algorithms like Minimax or AlphaBeta, they are, we're not trying to get too complicated. So we're going to talk about two-player games. So I make a move, then you make a move. Zero sum, so it's a win, lose, or draw, essentially. They are alternating move. Perfect information, so we know everything about the current state of the game. They are deterministic, so there are definitely board games like Monopoly or Backgammon where we have dice. We're not going to be looking at those because the Minimax algorithm by itself does not work for games with chance in them. We would have to modify the algorithm to do that, and they're discrete, okay? So, who knows what this computer is called, or who this person is? Maybe some of the older people in the classroom. Okay, hand up, don't yell it out. Yeah, I saw your hand first. And do you know the name of the computer? Deep Blue. Okay, so you got the company correct at first. So this is IBM's Deep Blue, and in 1997, this was up to the time, other than like the Terminator, I guess, the biggest news for AI that had ever existed. For a long time, this was sort of the holy grail of AI research, which was creating a computer program that was able to beat the world's best human at chess. And since 1997, no human has even come close to beating the world's best computer program at chess. And using the techniques that we'll learn in this and the next lecture, I'm not saying that right out of the gate you'll be able to beat the world's best human, but if you did apply these things to a game like chess, unless you are a grandmaster, you would certainly be able to beat yourself at a game like chess. And this over here, they used the Minimax algorithm with AlphaBeta pruning. But the thing they had on top of what we'll learn today is they had a lot of custom hardware, just like how nowadays there's custom out there like neural chips and all this stuff for computing deep neural networks in hardware. This one actually had hardware specific to evaluating chess positions. So they took their algorithms for saying, okay, there's no way we can evaluate all the way to the end of a chess game, so who's winning? And they took that algorithm that they had, or that heuristic function, which was a guess at who's winning, and actually put it into hardware, so it was like, 100,000 times faster, or something like that. So how did they make that machine? What is the thought process into creating a machine that could beat someone at chess? So how can we design an algorithm to play a two-player alternating move game? Well, one very obvious thing you might think of at first is let's just hard code some rules, right? Like for a game like chess, okay, move your pieces toward the center. If it's a checkmate, that's a really good thing. Maybe you're assigning value to pieces, so if you can just take a piece that has a higher value than your piece, do that. It turns out that, yes, you can make an algorithm like that with a bunch of rules that you know about the game and just run it, but it turns out that that will very quickly plateau in skill level, right? So you'll get something that like really, really quickly does okay, but it will never do better than okay, and we'll see why that is. What if there's like thousands and thousands and thousands of if statements? Like, you can read all these chess books and study positions. Like, if it's this position, then do this move. If it's this position, then do this move. This suffers similarly to the first one, where it's like, okay, analysis, strategy, tactics, if-then statements. What if, for example, we change the rules of chess slightly? Now, all of that would be useless. All our analysis, all of our hard-coded stuff would all be useless. We're trying to make an algorithm where we can just give it the rules of the game, and it would be able to play pretty decently from that. So, if you've been paying attention to the course so far, we've been doing this thing called search, right? And what does search do? Well, it tries some actions, so it like looks ahead to see what it can do, and then evaluates those actions to see which of those is better. So that's what we're going to try first. So let's try this like look ahead and evaluate. So I've got some state of the game right here, and then I'm going to generate actions and create new states, just like our single agent search did. So let's have a look. So generate a list of actions from a given state. And this state, unlike the search we've been doing so far for pathfinding, maybe this is like a chessboard or something. Evaluate those actions based on features of the resulting states. So we will eventually have to evaluate the state of the game, right? And so it turns out that evaluation is one of the hardest parts of this. Why? Well, because if this is not the end of the game, well, okay, if it is the end of the game, it's very easy to evaluate, right? Have I won? Have I lost? Or is the game a draw? That is the end of a game of chess, for example. If I win, it's either like a 1. If I lose, it's a -1. Maybe it's positive infinity, negative infinity, some big number. But it's easy to evaluate the terminal state of a game. Terminal meaning there are no more possible actions, right? But if it's not the terminal state of the game, if this is like the first, this is the opening state of a chessboard, and this is after you've moved your first knight, for example, how do we evaluate that, right? It's a really hard problem. So applying an evaluation function, especially earlier on in the game, is a hard thing. And so you do the action which has the highest evaluation. So here would be the algorithm if we wanted to do something like that. Very, very simple. I'm sure you could all write this algorithm. It's really intuitive. So this look ahead and evaluate takes in a state. And what we're going to do is we're going to try and find the maximum of something. So in order to find the maximum of something, we're going to set some initial value to -infinity. And we're going to record the best action here. I'm just calling it null right now. And then I'm going to have some function on my state called getLegalActions. And so, you know, in a game like chess, there are some actions that are legal. Like, I can't just take my pawn at the beginning of the game and capture the king, right? That wouldn't be a very fun game. So there are some number of legal actions that I could do. So for each of those legal actions, I'm going to create a copy of the state and do the action to it to create the child state. Then I'm going to assign some value to that child state based on whatever the game is, whatever function I have. Then if that value is greater than my current maximum value, I'm going to set the new maximum value to that value and record the best action, right? And then return the best action. That's it. Look ahead and evaluate. Really, really simple algorithm. So let's look at an example from tic-tac-toe, right? So here in tic-tac-toe, or noughts and crosses if you have to be from England, or X's and O's, whichever game, whatever name you call it, here's my current state. And let's say I am the X player, and so X is to move. So X can move either in the top here, in the middle, or to the right. So look ahead and evaluate is going to try each of those. It's going to try placing it in the middle. Oh, that was pretty good. That's a really good evaluation because I'm winning the game, right? Down here, I'm going to try putting up top. Well, what's the evaluation there? Well, I've got to have some function that, you know, maybe it's, if I win, it's a 1. If I lose, it's a -1. If neither person has won, it's a 0. So maybe this is a 0. It doesn't really know how good this state is. And similarly, this one over here also would get a 0 in this case, or whatever your function is. Just keep in mind that this evaluation can be very easy in the case of you've already won, or kind of difficult when you haven't, because you're only doing this look ahead. What are my actions, right? I'm not going any further than that yet. Okay, well, we can see the limitations of this. What's the good of just looking at my next move? Well, if you're right next to the end, it can be pretty good. But if it's not, and we're usually not, then it's not going to be great. So how about just searching the entire game tree, right? Just like we had a search tree before with our single agent search, the game tree exists for these games as well. But how big is the game tree? Well, we talked about this already. So B would be the branching factor, which would mean the number of possible actions that we could have for a game, or at any state of the game. And then the game is going to end after some number of moves, right? And so D would be that search depth. And if I've got B possible things I could do for each of D possible depth, then this is a huge, huge search tree. So it's very unlikely in practice, unless we are playing X's and O's, in which case there were only about 10,000 possible states or less, we could just search the entire game tree of tic-tac-toe, right? But that's not a very interesting game. We want to look at games where it's just not trivially searchable. So we looked at this before, so I won't spend a ton of time on this, but we talked about state spaces and action spaces. And if we look at tic-tac-toe really quickly, I'll just let this play through. We've got 3 possible values for each state of the board, and there are 9 states of the board. So we've got approximately 3 to the power of 9 possible states, right? So could we search over all of those possible states? Yes, we could do that. But for chess or Go, we looked at this already. these are gigantic numbers, right? And we don't yet have computers fast enough to be able to search this in a reasonable amount of time. So let's just let this finish out, and we can see, I think it's like 10 to the power of 42 or something like that. Yeah. So a lot of states for chess, and Go is even bigger. So I'll just fast forward to this, where, you know, we've got 10 to the 43 possible states for chess, 10 to the 172 possible states for Go. But as I did say in a previous lecture, this is the number of possible states. The game tree is searching the number of possible ways you can take actions, which is much bigger than that, right? Because you can get to each possible state in a huge amount of different ways. And so the game tree is what we're really concerned with when we talk about searching the entire game tree, right? And I don't know if the new like Mac M4 is good enough to do this, right? But probably not. And so we've got to just say, okay, we're not going to be able to search the whole game tree. That is not a reasonable thing. So if we combine these two ideas, we can't search the whole game tree, but this idea of looking ahead was really promising. So let's look ahead as far as we possibly can. And when we talk about as far as we possibly can, we're talking about within some constraint. Usually that constraint is like a time limit. So for example, if you're playing a game of chess and you might have 10 seconds per move, right? You got to hit the little clock every time you do it. Then your as far as possible would be look ahead as far as we can in 10 seconds. Okay, so we've got some constraint, but we don't have infinite computational resources. So for example, in this case, maybe we can look at 20 different nodes or something like that, and then evaluate them, and then look back. But unlike single agent search, now what we have is a completely different situation. Because in this game, I've got two different players taking turns, taking moves. And these players are actually competing against each other now. They are not cooperating, right? So in a single agent search, every action I take, I'm trying to get the best path to the goal. But the other player is certainly not going to try and help me get to their victory position. Okay, so let's have a look at what's going on. We've got one player, or player one. So we're assuming a two-player game here. And I've marked player one in blue. And player two is going to be in red here. And what's going to happen is, let's pretend that I'm player one and someone in the audience is player two. So these are the possible actions that I could take from the starting state of the game, and then it's your turn to move. And then these are the possible actions that you could take. And then it's going to be the possible actions that I could take, and then you could take. And so we're going to build this tree via alternating moves. And then what happens is at some point, you know, this would be player one, player two, player one, player two, until our search reaches a point where we've run out of time or resources or something. And so we say, okay, I'm going to apply some sort of evaluation to this state. So either a time limit has been hit, a computational resource has been hit, or the end of the game has been hit, right? That one can happen as well. And then I'll apply some evaluation function. And then it's the job of the algorithm to choose which action should you take if these are the evaluations, right? So the algorithm just trusts the evaluation. So it's really important to have a good evaluation function, but it may be difficult in some cases. So let's just look at this case. I just put in some random numbers here that give us some interesting properties. And so what we're going to do is we are going to be player one. So we are all player one now. So what we are interested in as player one is getting to the maximum evaluation state down here. Right? We look at all these evaluations. They are from the point of view of player one. So bigger here means better for player one, or for us. So I want to get to the best one. But here's the thing. The other player is trying to get to the lowest one, right? Because if it's better for me, this is a zero-sum game. So they're trying to get to the lower one, and I'm trying to get to the higher one. So let's see what happens. So instead of player one and player two, we're going to call these the maximizing player and the minimizing player. Because one is trying to get to the max values, one is trying to get to the min values. And this is going to be a depth-first search algorithm. Okay? So we're going to go down the left-hand side because we're just trying actions in order from left to right, however we've tried those actions. So in this case, we start at the root node. I'm going to try and minimize something, but I don't have a value here yet. Then this player is going to try and minimize something. So down here, the minimizing player has hit the evaluation nodes, and they're going to say, okay, I want to choose the minimum of these two. Pretty easy. So the minimum of 2 and 6 is just 2. Now, the search will say, okay, this player is done with their turn, so it goes back up to the top, and then it comes down here. This player still needs to have a value here in order to operate, and so the minimum player then gets called, and it's going to take the minimum value of 1 and 8, and then return that, and then the maximizing player is going to take the maximum of those two, which is 2, right? So we didn't actually get to the state where we capture the queen, because the other player is going to take some actions that prevent us from doing the good things, okay? So one player is going to try and maximize the return value from the other player, and that's going to alternate or recurse until we get the resulting value. So this was the look ahead and evaluate function for just one single depth. And so you can kind of think of this as, well, this is one look ahead and evaluate, where we're maximizing, and then this person is doing look aheads and evaluates for minimizing. So we're going to separate this into two different functions, the max value function, and eventually I'll say the min value function, right? So max value for a single depth, what would that look like? Well, it's kind of what we just did. I'm just shortening it here. So this v, that is the value. That's going to start off as negative infinity. And then for c in children s, that just means for every child. So before, where I had this longhand form of saying, okay, create the child, do the action, that gives us the child, do the legal action. For here, I'm just iterating through the children. It's just a shortcut, but it's the same thing. So v prime, that is going to be the evaluation of that child node. And then I just say, if v prime is greater than v, then v equals v prime. So I'm just taking the max. That's it. So that's the max value for a single depth. But you can see here that when the max, initially, when the max value person started, there was no value here. And if there's no value here, then it's not an evaluation node, so then the min function has to be called. So what we actually do is, instead of just a single depth, this is the full tree version, where we keep going down and down and down until we get to a terminal state. So a terminal state here, again, is one where the game is over, right? So the game is over if I'm in checkmate, or I've gotten a connect 4, or I've got 3 in a row in tic-tac-toe. That's a terminal state. So if the max value function now says, okay, if I'm at a terminal state, just apply my evaluation function, because there's no more search to be done at a terminal state, right? So if this is a win for max player, return a 1, for example. Otherwise, we're going to do that maximizing. So if it's not a terminal state, I've got more search to do. So have this v equal to negative infinity, and then for each child, instead of the evaluation here, I'm not doing the evaluation because this isn't a terminal state, because I just checked up here, then I'm going to call that min value function on this child. And then if the return of that value is greater than my max, set it to the max, and then return that value. And then I just have the min value, which is the opposite of that. Instead of taking the maximum, I'm taking the minimum. And so in order to take the minimum over here, I've got a positive infinity that I start with instead of negative infinity, and then I'm checking, is v prime less than v? So max value calls min value calls max value. Got it? Okay, so that's the algorithm that we just looked at, but visually. Now, this is for the full tree, and we just said, I can't search the full tree because the new Mac isn't fast enough yet, despite what Apple is saying, right? So what do we have to do? Well, what have we done in the past when we can't search all the way? We introduce a depth limit to the search, okay? So I have a new parameter here. Instead of my max value and min value just taking in a state and then trying to search all the way to the end of the tree, we're taking in a depth. And so the only real change here, if you can look, it's not much of a change. The algorithm itself doesn't change. I'm just accounting for this depth limit. So if now I'm evaluating the state if the state is terminal or the depth is greater than whatever max depth that I've set, right? So if I only want to search down to depth 4, as soon as I get to greater than depth 4, sometimes you want to do greater, sometimes greater than or equal to. But as soon as you get to depth 4, you're saying, okay, I've hit my depth limit that I've set, just return an evaluation. And down here, the only other thing is that whenever I recurse, because this is technically a recursive function, right? Because it's calling itself. I'm going to pass the next depth down. So I have a variable which keeps track of the depth. And whenever I call a new recursion, I'm just saying, okay, pass the next depth. So initially you're going to pass depth 0, then it'll go depth 1, depth 2, depth 3, depth 4. And so you can keep track of that. Now, these are two different algorithms. The max is calling the min is calling the max. Max, min, max, min. Oh look, we have a Minimax algorithm. Okay, so what has happened here is I've taken these two functions, and what I'm going to do is wherever I want to check, I'm going to turn them into a single function, and that single function will be the Minimax algorithm. Okay, and in order to know whether or not I'm maximizing or minimizing, I'm just going to have an additional Boolean variable that these didn't need. So because one of these is maximizing and one is minimizing, you don't need to keep track of whether you're maxing or minning. But in the actual Minimax algorithm, you do. So what I did is there's just one more variable here called max, and that is if it's true, I'm maximizing. If it's false, I'm minimizing. And then down here, I've got if max. Well, you've seen this before, right? And instead of me saying v prime equals something, if v prime, I've just replaced that with a maximizer, right? So I've gotten rid of that, that variable. And so if I'm maximizing, do the maximizing, else, then I'm not maximizing, so do the minimizing. And here, when I call max, I know that my next recursive call to this function, I should be minimizing, so I pass in false, so that it minimizes next. And when I'm minimizing, I know that I'm going to be maximizing next, so I pass in true. Okay? And my initial call to this function is going to be with the starting state. Now, this doesn't mean it's the starting state of the game. Like, you're not always passing in the first state of a game of chess where all the pieces are lined up. You are going to pass in the starting state with respect to what is the state right now that I actually want to make a decision for. So if it's the middle of if it's the 12th state of a game of chess, you're passing in that one. And the initial depth is going to be 0. So 0 is the root node in the search. And the player who I'm wanting to decide on, well, that is obviously the maximizing player, right? So I'm passing in true first so that the first move that we do is a maximizing one. And so that's the Minimax algorithm. I look at what I can do, what the opponent can do, what I can do, what the opponent can do, and I am assuming that the opponent is pretty decent, so they are minimizing this evaluation function, and I am going to be maximizing that evaluation function. Now, this algorithm is kind of long and unwieldy sometimes. It's not that long. Okay, 13 lines of code isn't that long. But as computer scientists, what are we always stupidly obsessed with? Lines of code. Make it shorter, make it shorter, make it shorter. Just for completeness, here is the Negamax algorithm. Nega meaning negation. And you'll see why that is in a second. And this is just like, you know, a shortened version of the exact same algorithm that's more complicated to understand. And so that's why I don't show it first. But essentially, if you take the fact that the maximum of A and B is equivalent to the negative minimum of negative A and negative B, and here you can say negative negamax and take the max of those, then you can do this all in one step. Okay? So that negative value is where these negatives comes in, and so this is the equivalent algorithm. Trust me. Do an example out. It's really interesting. I do not recommend implementing this on the assignment. I always recommend start with the long form that's easier to understand and easier to program. But you can save a few lines of code if you do that. That's the last I'll say about Negamax. Ideally, it doesn't show up in your assignment. And I will tell you that the shorter the version of AlphaBeta, or sorry, Minimax, that you end up implementing in your assignment, the harder it will be to debug. Every time you eliminate a line of code, you eliminate a debugging variable, right? And you just make it a bit harder. I think I saw a question. So this is, right now, we are just passing in a maximum, we're going to choose some sort of maximum depth, right? So I'll get to that toward the end of it, but the deeper it is, like if I say, hey, run this algorithm to depth 2 versus depth 10, it's going to take a lot longer to run to depth 10, right? So the running time of this algorithm, yes, is completely dependent on the branching factor and the depth that we search to, okay? So some properties of Minimax. It is complete and optimal. It will find a solution, meaning it will find the best move that you should do up to a given depth. Each player plays a best response to the possible actions of the other player, right? So if I'm looking at what the opponent can do and choosing the best action for them, and then looking over that and choosing the best thing I can do in response to that, then that's literally the best response. We're doing the same thing that we did in that matrix game, except now we're doing it in a game that's recursive rather than one single action, right? It's very difficult to like put chess into a matrix form game because there's multiple actions. So because we are best responding, what does that mean the Minimax algorithm will give us? Hand up, don't yell it, yep. Nash equilibrium. Both players are best responding to the other player. Therefore, this is going to play the Nash equilibrium. And so for two players, finite, zero-sum games, a Nash equilibrium exists. And just recall that in a Nash equilibrium, each player is best responding to the other. Neither player can gain by deviating, and neither player has any regrets. But we also did see that the Nash equilibrium doesn't always get us to the maximum possible value because there could be multiple Nash equilibria, right? So one path through the game tree, maybe there's some tiebreakers or something like that, and if we have gone over here, we may have gotten a better value, but we are still within a Nash equilibrium. And playing a Nash equilibrium is, in general, a very strong strategy because how could you be stronger than not having any regrets, right? Now, playing a Nash equilibrium, again, doesn't mean that this is the fastest possible way you could beat someone in chess. Why? Because the Minimax algorithm assumes that your opponent is equally as strong as you. In fact, you're also assuming that they're using the same evaluation function as you. So if you are writing the Minimax algorithm and you play it against a really bad opponent who's just like, this is their first game of chess, you're still going to be assuming that they're like a grandmaster, right? And so maybe there are some strategies in a game that could beat a very weak person very quickly, but you're not taking those. So just remember that the Nash equilibrium doesn't mean this is the best thing against every possible opponent to beat them the fastest. It just means, in general, this is a strategy that you should use against equally skilled opponents, etc. That's kind of a hand-wavy way of looking at it. Can we improve the Minimax algorithm? And the answer is absolutely, and it's really cool. So let's have a look at this example again. It's the same example that we did before, but we're going to step through it a little bit slower. So we start up at the root here. Max looks down at this value. It's not a terminal node, so it calls min. Min looks down at this value. It is a terminal node, and so it applies an evaluation to it. That evaluation happens to be 2. Okay? Then, what do we know when this is a 2? Well, I've spoiled it, but if this is a minimizing node, and this is a 2, we know that this node will have a value of less than or equal to 2 by the time we're done with it, right? Because anything that's bigger than it, we're going to ignore. So this is going to be less than or equal to 2. Let's say, oh look, it's a 7. That's not less than or equal to 2, therefore this is a 2. Now what do I know? Well, I know that the value of the root node is going to be at least 2. No matter what happens over here, this is going to be at least a 2. Because if I'm taking the max of both of these, nothing here that's smaller matters, right? So this is going to call here, it's not an evaluation, it's not a terminal node, so Minimax calls, or sorry, min value gets called, and now it's looking at an evaluation node. So down here, look at this. If this is a 1, that means that this is going to be less than or equal to 1. But I know that this is going to be greater than or equal to 2. So, can any value of this change my computation? It literally doesn't matter what this is. It doesn't matter if it's smaller. It doesn't matter if it's bigger. Why? Because I know that I don't need it. Because the only things that would change my mind up here is if this were greater than 2. So that means I can just disregard all other computations on this branch. Okay? See how that works? If I know enough to know I'm going to need something that's at least this much or at most this much, and the opposite can happen as well, right? So if someone says, okay, if the minimizer says, well, I know I'm going to need something that's less than or equal to 1, right? And then there's a 7 or something like that, it can have a similar value. So yeah, I can just disregard that entire computation. And if you think about this in terms of the full size of the tree, this can have absolutely huge savings. So I know that this value is 2. And this is called AlphaBeta pruning. And so AlphaBeta pruning is not a different algorithm from Minimax. It is an optimization to the Minimax algorithm. So let's be pedantic here for a second, and then we'll just start saying what everyone else says. Technically, AlphaBeta pruning, if we are applying this to Minimax, the algorithm should be called Minimax with AlphaBeta pruning. But colloquially, people have just shortened this to say the AlphaBeta algorithm. Okay? So Minimax adding AlphaBeta pruning, it's Minimax with AlphaBeta pruning, but we're pretty much just going to call it AlphaBeta for the rest of the course. So it maintains all the same properties of Minimax because it's going to give us the same answer. We're just discarding things that don't matter. So it's strictly better, right? It's one of the few optimizations where I was going to say you don't need any more memory. Turns out you need 2 extra variables, but that's not so bad. Cutting off branches of the search tree can yield exponential savings. And so this is what we're doing. We're taking a tree that has a bunch of stuff we don't want in it or don't need, and we're pruning it to make it contain only the things that we do want. So AlphaBeta pruning uses the Minimax algorithms. We introduce 2 new variables. Who can guess what those variables are? Alpha and beta, right? So alpha and beta are the best alternative for max on this particular path through the tree, and beta is the best alternative for min on this particular path through the tree. And so alpha beta, yes, in that simple example, it's very easy to understand. But when you get into bigger trees, it's kind of tough to visualize. So what I like to say is that alpha and beta are like the top end and bottom end of a window that is getting narrower and narrower as the search goes on. And it's getting narrower and narrower because you get more and more information as the search goes on. And you can discard certain nodes if the information in a very specific way is outside of that window. Okay? So here was Maxvalue and Minvalue with just Minimax. But now let's introduce alpha and beta. So it's not a big change, but it is kind of hard to remember, okay? So we're introducing alpha and beta up here as 2 new parameters. I've just shifted depth over. And then we see here we've added 2 lines down here. Those 2 lines are, if the value that we just got is greater than or equal to beta, then return. So this early return statement is going to cut off this branch of the tree because I'm in the middle of generating all the legal actions, but I say, no, return this value immediately. If it's not a cutoff, then what I have to do is I say, okay, if this value is greater than my current alpha, then set alpha equal to v prime. And that's that narrowing of the window, okay? And it's just the opposite for the min value function. It's the beta version of that. So, and since alpha is maximizing and beta is minimizing, we pass an initial value of -infinity in for alpha, and we pass an initial value of +infinity for the initial beta, and our initial depth is 0. So now I've done this meticulously handcrafted example that has some nice cuts and stuff in it, so we're going to walk through this whole example of alpha beta. If you go online and you look at alpha beta visualization, they did what I probably should have done and like actually write a program that generates this sort of thing. But I did this all manually in PowerPoint. So what we're going to do is we're going to call the root node with the start state, -infinity for alpha, +infinity for beta, and 0 for the depth. And so what's going to happen is we're going to go down through the tree like this, and I'm going to keep track of the values. If you see a negative with no number here, it means negative infinity. If you see an alpha or a positive with no number, it means positive infinity. And I apologize that this is kind of small for the classroom. I hope that you can see it. If not, then you'll have to look at the video later. So what we do is we call with the max value. That looks down. There's no evaluation yet, and so the min value gets called. Okay, but now we have our v is positive infinity because a min node is going to be minimizing, so we have that positive infinity. But alpha and beta don't change until we've actually done something with an evaluated value. So then min calls down here. Oh, look, it's not an evaluation, so min calls max. Max calls min. Okay, now we've gotten to the point where we're actually looking at some data. So for our convenience, I've listed the algorithm up here again. So these three things are going to happen, and then I'll press a button and the values will update. Okay? So here's the value that we have. This is the new v prime. So if v is positive infinity, alpha is negative infinity, and beta is positive infinity, let's do these checks. So is v prime less than v? If it is, then set v equal to v prime. Well, v is positive infinity, so yes, it is less than that. So we're going to check, we're going to set v equal to 8 once this is done with. Is v prime less than or equal to alpha? If so, return. Well, alpha is negative infinity, so there is no cut yet, right? If we don't have an alpha yet, how can we do an alpha cut, essentially? So no, we won't do that. Is v prime less than beta? Yes, because beta is positive infinity. So when we're done with this, v is now equal to 8, alpha is still negative infinity, and beta is 8. Now we go back up here, then we check the second one, right? So we look at 7. Is 7 less than or equal to v? Yes, it is, because v is 8. Is it less than or equal to alpha? No, it's not. Is it less than or equal to 8? Yes, it is. So this gets changed to a 7. So we just found a new minimum, basically. Now this one is done. So this v is 7, alpha is negative infinity, and beta is 7. So we go back up because we've done everything. This one now has the value of 7, right? So if this has the value of 7, this is the max value algorithm. Is v prime greater than v? Well, v, for a maximizing node initially, is negative infinity. So yes, 7 is bigger than negative infinity. Is it bigger than beta? No, it's not, because beta is still positive infinity. Is it greater than alpha? Yes. So we're going to set v and alpha equal to 7 here. And now we're going to go down. This one, you can see now we actually have a value of alpha to work with. So something to keep in mind is that these values, they are passed by value, not passed by reference. So the values only get passed downward, not back up. Okay, so that's something that's hard to visualize at first. And we can only work with information from higher in the tree, not from lower in the tree. So here we go. Now we are going to look at another node. So we've got we've got 3. Is 3 less than positive infinity? Yes. Is 3 less than or equal to alpha? Oh, look, we have a value of 7 now. And so what this means is, if we want to think about it intuitively, up here, we are maximizing, and we currently have a 7. If this is minimizing, and this is a 3, we know that this thing is going to be at most a 3, and something that's at most a 3 will never be bigger than at most a 7, and so we can cut it off. We don't need to look at anything else. This could have a million branches, and we don't need to worry about it. So this value gets propagated back up, and then we look at the max value. So now we have these values, and this is a 3. So is v prime greater than v? Well, v is a 7, so no, it isn't. Is it greater than beta? Beta is positive infinity, so no, it isn't. Is it greater than alpha? No, it isn't. So this one essentially just gets the value of 7 now. But we were able to save the computation on this branch of the tree. Not a lot of savings yet, but we'll keep looking. Now this one has a value of 7. We're going to do the same things, and what we find is that the value and the beta get updated. So now, when we go down, we'll have this value of beta. to work with, where we didn't have a value of beta to work with before. So now we come to a maximizing node, but there's no evaluation, so we go down to a min node. Now we're looking at this. So 9. Is 9 less than positive infinity? Yes. Is it less than or equal to alpha? No, because that's negative infinity. Is it less than beta? No, it isn't. So the only thing that gets updated is v. Next, we're going to look at 8. Is it less than the value? Yes, it is, because it's 9. Is it less than alpha? Nope. Is it less than beta? No. And so v gets updated, but nothing else. And so now this has the value of 8. So what we're going to do here is say, okay, is v prime greater than v? V is negative infinity, so yes. Is it greater than equal or to beta? Oh, look at that. Yes, it is, right? So beta is currently 7. So up here, we're maximizing knowing that the thing will be less than or equal to 7. And here we're maximizing knowing it will be at least 8. And so this is the opposite cut. This is a min cut or a beta cut, okay? So if the check to beta is true, then we do a beta cut. And so this, we don't need to do anything down here. And if this was 400 depth deep, it doesn't matter. We can save all that computation. This gets the value of 8, and of course 8 is greater than 7, and so this is not updated. So now this gets the value of 7, because it's the minimum of 7 or 8. So I'm going to just try and speed up a little bit. So up at the top here, now what do we have? Well, now we have a 7 to work with up at the very top. So is it greater than or equal to v? Yep, because v is negative infinity. Is it greater than or equal to beta? No, we still haven't set a beta. Is it greater than an alpha? Yes. So now we're going to be starting the right-hand side of the tree with a value for alpha. And so if we have values for alpha and beta, that's our window. So now this whole side of the tree is going to have that maximum side of the window. It's still infinite in this direction, but we'll see what happens. So we go, sorry? Okay. So we go down, down, down until we always go down until we get to an actual evaluation node, otherwise nothing is happening. Here, we get to a 1. This is a minimizing node, so we say, is v prime less than v? Yes, because v is positive infinity. Is it less than or equal to alpha? Look at this, it is. So we've got a cut down here. Now this is where it actually gets quite difficult to intuitively reason about why this cut happened, right? Because it's like, well, this is a min for this and a max for that and a min for this and a max for that, which is why I just like thinking of it as a window, right? And when we're doing an alpha check and it's outside, well, then we can just cut. So we don't need to look at this value. But we do have a value of 1 now for this, and this is maximizing, so this is going to go down. And we're going to say, okay, this value of 6, is it less than v? Yep. Is it less than or equal to alpha? It is again, right? So we can cut this. We don't need to look at that. Now this one has a 6. Is the 6 greater than v? Well, v is currently 1, so yes. Is it greater than or equal to beta? Beta is still positive infinity, so no. Is it greater than alpha? No. So we're just updating that value of v. Now this node has the value of 6. And finally, we get to see a big old cut, okay? So now we're here and we have v is 6. So yes, I got to do this step again where I say, is it less than v? Yes, but nothing else matters. So this just gets the value of 6. But look at this. This is a 6. And just like our first example, this is identical to it. This 6, is it less than v? Yes, so v would update. But is it less than or equal to alpha? Yes. And so we can stop and return. And we don't need to look at anything down in that tree. Why? Because the only thing this tree could do would be to help this one get a smaller value. But the value we had over here of 7 is already bigger than this value. And so smaller values we don't care about. And so that now gets the value of 6. And we're maximizing a 6 versus a 7. And so this gets the value of 7. So we know now that the value of the root node is 7. Now what we'll see in a little bit is that, sure, okay, I know the value of the root node. Which action should I take? So we haven't actually recorded the action here, right? I could have 20 actions up at the top. All I know from this algorithm is what the value is. I didn't record the most important thing, which is what I should actually do. So at some point in a bit, we're going to talk about how you actually record that action. But for now, let's talk a little bit more about just the algorithm. So in Minimax tree search, the number of nodes searched is b to the power of d. And there are papers out there that talk about this. And with AlphaBeta applied to Minimax, the nodes searched is approximately 2b to the power of d over 2. So that means you're approximately searching the square root of the number of nodes you use to search. And the square root is it's like an exponential savings, right? So that's excellent. And that means you can search to about double the depth. So if you could search to depth 7, and now you can search to depth 14, think about the difference in skill of a chess player who can look 14 moves into the future instead of just 7 moves into the future. I can't even look 3 or 4 moves into the future. I'm not a good chess player, right? And so maybe if you had a program that was okay with Minimax, now you might have a program that beats the world champion. I'm exaggerating there a little bit, but you don't have a chance at beating the world champion without this AlphaBeta optimization. Okay, so this is our max value and our min value algorithms which have alpha and beta in them. And so of course we want to turn this into a single recursive function rather than 2 functions. And so we just do what we did the last time, which was we just put an if statement with a max, right? So this function now is Minimax with AlphaBeta Pruning, which has a maximum depth and a maximizer, right? So, okay, if I'm maximizing, do the maximizing part. If I'm minimizing, do the minimizing part. And I have made a terrible typo here. These are supposed to say AlphaBeta, because this is now calling AlphaBeta, right? So yeah, this is just wrong. And but I hope you know what I mean when I turn this into this. So I've got the correct version on the following slides. Now, this is not a lot to type, but we are often concerned with shortening our algorithms, right? So not only are we concerned with shortening our algorithms, but me as an educator, I am concerned with your understanding of this. And so something that always happens, and it's fine, like you might say, oh, I didn't like the way that Dave explained that. Let me go to Wikipedia. Let me go to some other resource, a textbook or whatever, that's going to have a possibly different version of this algorithm in it. Now, it'll still give the same result, but what I've found over the years of looking at different versions of AlphaBeta is that they can look wildly different, okay? This is sort of I'm so sad that this is wrong because I'm so embarrassed now, but all you gotta do is change the min value to AlphaBeta and then put the maxes in there. So this looks very different than the algorithm that you'll find on chessprogramming.com. It looks very different than what you'll find on Wikipedia, and maybe very different than what ChatGPT would spit out. So what I'm gonna do is take you from this, which is correct, but very verbose, all the way to the shortest possible version. And what you'll see is different versions that you'll see on different websites just stop at a different station along this journey to minimizing the amount of lines in AlphaBeta, okay? So hopefully this will help you understand that. So I'm gonna do this first by looking at max value. All right, so I hope I remember all of this because it's kind of complicated, and if I go a little bit quickly, just let's save questions till the end because there's quite a bit to go through here. So the first thing I'm going to do here is just reverse these 2 lines, okay? So this will not have an effect on the outcome of the algorithm. It'll just make it slightly less efficient. Why? Because if I'm returning after I set this, then I'm just doing one extra little check, okay? And why am I doing that, Dave? Why are you just reversing 2 lines? That'll be apparent in a little bit. So I reverse those 2 lines. Next, if I reverse those 2 lines, now I am also storing this new maximum in alpha and not just in v prime, sorry. So instead of choosing is v prime greater than or equal to beta, I can now change that to is alpha greater than or equal to beta. Just by that reordering, that lets me do this, Okay, so reordering allows us to compare alpha, which will not now store the maximum of v prime. Now, because that was the v that I was storing, instead of returning v, I can return alpha, and this will give me the same result. Okay, so we can now also store alpha since it is storing max of v, right? So that's just a reordering that lets me do that. Now let's have a look at this. V, because we're now using alpha, v is now just like a temporary variable where I'm storing this like max calculation placeholder. So I can get rid of v altogether, right? And instead of returning v, which was previously storing this value, now I can just return alpha instead. So this version, which is 2 or 3 lines of code shorter, computes the same value, okay? So what am I doing next? Here I'm saying v prime is equal to this thing, and then saying if v prime is greater than alpha, alpha is equal to v prime. Well, this is just a maximum calculation, right? So instead of having these 2 lines of code with this temporary variable, just put in a max. So I can replace that with a max. So alpha is now equal to the maximum of the previous alpha and the min value call. So that's another line of code that's eliminated. And now let's remove that white space, and this is the most compact version of max value, okay? And it looks completely different because you're like, where did v go? Where did all those variables go? Is this the same algorithm? But now you can see that yes, it's actually returning the same result. Now let's do something that will not become obvious why we're doing it for a little bit, but see this return alpha? What's a different way? Thank you. What's a different way that I could return alpha here? Does anyone see? Without a return statement? Yeah. No, I'm not. I want to remove the return statement here. It's okay. This is, yep. Exactly, right? Look at the next line of code. So wherever I would have returned, if instead I just break, then the next line of code is return alpha. So this is equivalent, right? All right. Now you say, why would you do that? That will come into play in a little bit. So now I'm going to list the min value. So I've done the exact same derivation in reverse for the min, okay? So this is min now. Okay. So the same shortening can be applied to this. I'm just not going to step you through it because it would take too long. But look at this. Over here, I've got alpha greater than or equal to beta. Over here, I've got beta less than or equal to alpha. This is the same check, right? They're just reversed. So let's reverse it. Okay, now I've got alpha greater than or equal to beta. Okay, so if I've made 2 lines of code the same, you'll probably say, okay, now we can eliminate it somehow. But how can I can't eliminate it because it's part of the algorithm. But I still haven't combined this into a single algorithm yet, right? There's still 2 algorithms. So let's do that. We're going to combine them into the full version of AlphaBeta, where I've got a maximizer, or a maximizing variable. If max, do what we just did. Otherwise, do what we just did. But look at this. These are all duplicate lines of code, right? So here I'm saying, if max, do all this stuff. Here I'm saying, otherwise, do all this stuff. But I can actually take the max and put it inside the child loop. Because no matter what happens, I'm going to be iterating through all the children. So let's take the max stuff and put it inside the loop instead. And then if we do that, we get this, right? So now for all my children, oh geez, that's a throwback to the soap opera. For each of my children, now I've got the max inside here, and I've put it just in one line, because I can do it in one line now, right? So if max, alpha is equal to the max of alpha and the alpha beta call. If not max, beta is equal to the min instead. And now I've gotten this one check because both of my conditional checks were the same. So if alpha is greater than beta, break. And the only thing that was different here is up here I'm returning alpha if it's maximizing. Down here I was returning beta if it's minimizing. So I can just say if it's max, return alpha, otherwise return beta. with this trigram or whatever it's called. And so this is the final shortened version of AlphaBeta that many websites and textbooks are going to give you. And this is, without that derivation, it's like, that's so much harder to understand, in my opinion. Like, just the line, and it still confuses me to this day, how this same conditional works for both. I have to look at this for like 5 minutes to get that straight in my head. So this line of code specifically trips me up and is what I did not understand until I first saw the full version of the algorithm. And I had been writing AlphaBeta for years before I actually said, okay, I really need to understand this, and went from the full sort of naive version all the way down to this. So this is the final shortened version. It returns the value of the state. The result is the exact same as the long version. Here I say, implement whichever one you feel more comfortable with. Having said that, please don't implement this version. It's way harder to debug, and it's way less intuitive, in my opinion. Not only that, but this is only returning the value. We still have to keep track of what move I should do, and it turns out that in order, like when you have statements like this, alpha equals max of this, that doesn't let you do something like say, oh, if it's a new max, record the action, right? And so we're actually going to have to undo some of these line of code optimizations in order to actually record the action. So that's a downside of this version of the algorithm. Which action do we take? So far, we're only calculating the value. I need to record the action. But let's have a look at this. I'm calling this function with respect to the state that was up here, right? And so really, the only actions I care about are the ones that were made by the root player. I don't need to record what the best action is 20 moves from now. I want to know which action should I take. So what we're going to do is we're going to roll back those optimizations a little bit till we get to the point where I can say, if this is a new maximum and this action is being issued at depth 0, record the action. Okay, so that's what we're about to do. So here we go. I've got to undo some of this stuff. So around here you can say, okay, if max a equals max whatever, we're getting rid of that now. And we're going back to this v prime placeholder variable. And we need that placeholder variable to be able to know when a new max has been found, right? So when a new max has been found, I am now recording that action. I am saying if the depth is equal to 0, wherever I'm recording my best action, keep track of that, okay? So I need at least this much code in order to actually keep track of that action. Here, all right, this is the correct one that you should be looking at because this one actually records the action. And this is what I recommend implementing for the assignment. I'll get into more of that when the assignment comes. And it turns out what I actually recommend for the assignment is implementing base Minimax without AlphaBeta first, making sure it works and you're getting good results, and then implementing AlphaBeta. Why? Because Minimax and AlphaBeta return the exact same result. And if you implement AlphaBeta first and you get the wrong result, you're not sure if your algorithm is wrong or your usage of alpha and beta are wrong, right? So I always recommend do Minimax first. Once it works, then implement AlphaBeta. But here's the full long version, and it's still only 20 lines of code, right? So it's not that bad. Next, okay, well, in your assignment and also in real life, you may want to actually implement a time limit, right? So a depth limit is not a time limit because depending on the game, depending on the computer speed, depending on a bunch of different things, you might be able to search to depth 6 on your machine in playing chess. You might only be able to search to depth 4 on my machine playing chess. Or if you're playing Connect 4, maybe you can search to depth 20. But let's say I just wanted to search for 5 seconds. How do I do that? That's very difficult, right? If you think about it, like I've got to come up with some weird scheme for like, how do I approximate the number of nodes per second? Nope, iterative deepening, right? Iterative deepening solves everything. It lets us do what we did with iterative deepening depth first search, but guess what? This algorithm is called iterative deepening AlphaBeta. Iterative deepening AlphaBeta. How do we do that? for depth equal 1, 2, all the way to infinity, perform an alpha-beta search to depth d. When the time runs out, return the best action, here's the most important part, from the last fully completed search. Why does it have to fully complete? Because we cannot trust a search that didn't complete. Why? Let me try and draw this. I should really have a slide for this, but I didn't. So here we have the root node. Apologize, right? Let's say, here are my actions. Let's say I got a 7 here. Oh, dear Lord. Why am I looking there? I got a 7 there, right? I got a 3 here. Okay, I'm keeping track of the 7. Now I'm going down in this search and my time runs out. So I'm going to have to stop the search. Maybe this was my search to depth 5, for example. I'm going to say, oh, do this action. That's the best action. Look, it got a 7. But maybe by the time I got over here, that would get 1,000,000. Maybe that just wins me the game instantaneously. So until I have fully completed a search to a given depth, I cannot trust anything that AlphaBeta or Minimax tells me. I know what the best move is so far, but it is way more than likely that the full answer from the last completed depth, so if this is depth 5, my answer from the fully completed depth 4 is going to be better than my half completed answer from depth 5, right? Now, the intuition here is that if you can search deeper, you get more knowledge, so the move is better, right? So if I can search to depth 10, and you should actually try this once you get assignment 3 up and running. Take a program, make it search to depth 5. Take the same program, make it search to depth 8. The depth 8 search version will probably win 99% of the time because it can just get more, it gets to that move where the queen is captured, whereas the other one didn't, right? But you cannot trust a search that doesn't complete. That is so utterly important. But when the time limit is hit, I'm in the middle of a recursive function call. What programming technique do I use in order to escape a recursive function call? Right? No, please don't shout out answers. But it turns out that exceptions are to the rescue. And this is the only exception to the no exception rule in our course, if you want to look at it that way. So for assignment 3, you are going to be doing iterative deepening AlphaBeta. The AlphaBeta algorithm is easy. It turns out iterative deepening is just like the little bit trickier part. So I have basically given you the entire pseudocode for the algorithm here in the lecture slides. You're going to start by copying and pasting this and translating it into JavaScript. But this is actually kind of JavaScript. So in the config, you're going to get the time limit and a maximum depth. So in the UI, you're going to I'm going to say, let's, for example, search for 2 seconds or depth 10. And you're going to stop whenever the first of those hits, right? So you're going to have a variable, which is the current maximum depth that you're searching to. You are going to have the best action overall that you should actually play. You're going to have the current best action that the current best depth has found. And you're going to have the maximizing player. So is that the player placing the black pieces or the white pieces, for example? You're going to have an evaluation function, which takes in a state and evaluates that state from the point of view of a particular player. You are going to have the iterative deepening AlphaBeta function, and you're going to have the AlphaBeta function. So let's have a look at iterative deepening AlphaBeta. What you're going to do every time you call iterative deepening AlphaBeta, you're going to set the best action back to null because we're starting a new move, right, of iterative deepening AlphaBeta. I know nothing about any best moves so far. So I'm going to take the state, the current player who is to act at the state is the maximizing player. So if I'm about to move, I'm the maximizing player. Then we iterate through all the depths. So from depth 1 up to this.config.maxDepth, that might have to be a less than or equal to. I think I'll change that. Then I set the variable, right? So this is going to be in a class. So these are my class variables. So I'm going to record the current maximum depth that I should be searching to. This could also be a parameter into AlphaBeta, but I don't want it to be like 50 parameters long. So we're just storing it as a class variable. Then this is the important part. We're going to try calling AlphaBeta with these parameters. So state, negative infinity, positive infinity, depth 0 at first, and maximizing is true. So if what happens inside AlphaBeta, and this is very small, but essentially inside AlphaBeta, we are somehow going to check to see, has the time elapsed? If the time has elapsed, we're going to throw an exception. The way throw, try, catch works is that we're going to call this, if an exception is thrown inside this try block, it's going to skip over everything else inside the block and come down here and be caught. So what this does is, it says, try doing AlphaBeta. If AlphaBeta does not hit a time limit, then it will set the overall best action to the current best action. So AlphaBeta was actually able to complete the search to the current maximum depth. So for example, if this is depth 3, if AlphaBeta searches all the way to depth 3 and completes, then this says, okay, change the current best, the best action overall to the current best action. But if AlphaBeta to depth 3 stopped at any point before it completed, this will skip over this line, and the current best, or the this.best action is going to be the one that we set when depth 2 completed. Okay? So this is how we are able to do this programmatically. So there's a difference between the theoretical algorithm and then how you actually go to implement that in code, and this is the method from doing that. And then in the end, what you want to return from iterative deepening AlphaBeta is the best action. We don't really care what the value was, we just want to do the best action, right? But it turns out that, this is the whole algorithm just printed out in pseudocode. What you may want to do in order to debug your algorithm, if you don't think it's working properly, is like print out the values so that you can say, oh, that was a win, but it's got a weird evaluation function, etc. What I would recommend is actually doing this first. So this is the Minimax version with no AlphaBeta, and you can see that this is significantly shorter than the AlphaBeta version, so I would recommend doing that first. So as always, just knowing, what some exam questions could be here, knowing the relationship between Minimax search and the Nash equilibria, which we talked about for a bit, knowing the Minimax and AlphaBeta algorithms, of course, you would have to know that. Why is iterative deepening necessary for something like a time limit, right? Why do we need something like that? Now, we're going to pretend that iterative deepening is the only way that you could do something like a time limit, right? It's by far the most popular way. There may be something where you could call some weird system interrupt or something like that. But theoretically, with this algorithm, why is iterative deepening necessary? How does AlphaBeta pruning help Minimax? And if I give you a tree with those values on the bottom, fill in the intermediate node values, draw where the cuts are, etc., from actually doing out a Minimax or an AlphaBeta search.